Hi, thanks for your interest in our work. My name is Daniel Mox, and I'm a PhD student in the GRASP lab at the University of Pennsylvania. I'm going to be talking about mobile wireless network infrastructure on demand. In a typical multi-robot scenario, agents collaborating to complete a task need to exchange information in order to coordinate their actions. Many multi-agent algorithms assume the ability to freely exchange information and do not consider the impact control actions have on communication. This approach works fine in environments with existing network infrastructure. However, many robotic systems target scenarios where communication networks are unavailable or have failed. As agent actions drive them out of transmission range, they must either forego reliable communication or provide the infrastructure themselves by forming an ad hoc wireless network. This work focuses on the latter approach. Communication in teams of robots is a well-studied problem within the robotics community. Many early papers employed disk models and treated algebraic graph connectivity as a proxy for the ability of agents in the team to communicate. Later work by Jan used a more sophisticated probabilistic channel representation and placed network nodes so as to minimize end-to-end bit error rate between a fixed transmitter and receiver. In recent years, work by Fink, and continued by Stefan, enabled situational awareness by choosing configurations satisfying a packet routing optimization problem. Our approach builds on the packet routing strategy used by Fink and focuses on the team of robots that act as intermediate relay nodes, which we refer to as the network team. This team creates and sustains an ad hoc wireless network, providing service to a different team consisting of task agents accomplishing an objective. Our system operates independent of the specific task objective. Communication requirements are specified in the form of a desired data rate and reliability. We directly seek to maximize the performance of the network and target the application of our systems to robots equipped with widely available Wi-Fi hardware. In the next few slides, we will go into the detail of our methodology, which includes three main components: rate prediction, packet routing, and network reconfiguration. The propagation of wireless signals in realistic environments is affected by a variety of factors, including fading due to distance, shadowing from obstacles, and multipath interference. These factors combine to make it difficult to reliably predict the condition of the signal at the receiver. For this reason, we adopt a probabilistic channel rate model. The expected channel rate is constructed from generic relationships between received signal power, bit error rate, and channel rate, which can be combined to yield a function of node positions and tunable hardware parameters. The variance function captures the fact that channel rate predictions are less reliable as the distance between the agents grows. A plot of the mean and variance as a function of distance tuned for cheap Wi-Fi radios can be seen in the figure. Next, we turn to packet routing. Task communication requirements are defined by an intended data source and destination node, and a required rate with corresponding confidence. We now introduce a set of routing variables alpha that we control, which signify channel usage for each flow at each node. Then, the difference between data flowing into and out of a node, called the expected node margin, can be computed along with its corresponding variance. The intuition here is that the network is healthy and satisfies the communication requirements if the flow of data into and out of each node remains balanced. With the node margin constraints, we can pose the robust routing problem to find routing variables alpha that maximize the performance of the network. Here, the chance constraints guarantee that the required communication rate will be satisfied with the desired confidence, and the routing variables also respect channel usage restrictions. This problem can be formulated as a second-order cone program for fixed node configurations X, and a solution can be found in polynomial time with an available convex solver. For flows that require high confidence, robust routing exploits path diversity to overcome model uncertainty. On the other hand, For high-rate flows, robust routing utilizes the highest throughput channels. Next, we turn to the node reconfiguration problem. Finding optimal team configurations is challenging for a variety of reasons. The expected node margin is non-convex in the team configuration X. We do not assume that the channel model is differentiable. And it takes a non-trivial amount of time to solve the robust routing problem. To overcome these issues, we turn to analyzing the node margin constraints and define the function nu as the value of the node margin constraints closest to being violated. For a fixed set of routing variables, if the value of nu at a neighboring configuration x prime is higher than nu at x, more performance can be squeezed out of the network. Using this intuition, we define a local search algorithm that continuously seeks better network node positions. The algorithm begins with the current configuration of the team, as well as the optimal configuration cached from the last time the algorithm was run. We then find the optimal routing variables for the current configuration and for the optimal configuration. And in step 3, we use the value of nu for the optimal configuration as the benchmark to beat. Then, in the remainder of the algorithm, we sample network node configurations, updating the optimal if a better one is found. Putting all the parts together, we arrive at the following system for establishing a wireless network to support communication requirements. The system operates in a centralized manner on one of the network agents, which continuously runs each module. Updated routing variables are distributed to both task and network agents and are used to make packet forwarding decisions. Nodes in the network team continually update their position based on waypoint goals from the local search algorithm. We implemented our system in ROS and conducted simulations using Gazebo. In simulation, we do not transmit any packets, but rather test the ability of the local search algorithm to converge to a local optimum. In this scenario, 3 task agents patrol the perimeter of a circle while exchanging data, and a team of 3 network agents are deployed in support. Our system of mobile routers is on the right, reconfiguring as the task agents move and tracking a local optimum mirroring their configuration. The left side shows the performance of a fixed configuration, chosen to favorably cover the patrol space. The dashed black line in the plots is the required communication, while the delivered rate and confidence are shown in red. While the fixed configuration is unable to find feasible routing variables when the task agents are far away, our system successfully reconfigures to maintain a reliable network throughout the duration of the task. In addition to simulation, we also conducted an experiment with physical platforms. Our system runs on board a relatively modest autonomous quad-rotor platform with simple control and localization capabilities. We applied the robust routing solutions by performing route switching at the network layer. In the experiment, one task agent remained fixed, acting as a base station, while a second task agent performed a straight-line patrol. One network agent was deployed in support. We compare our robust routing approach with a naive strategy that ignores the network agent and seeks to maintain a direct link between the task agents. The performance of the network in each case is judged by using available network utilities to collect throughput and delay statistics. A top-down view of agent node positions is shown in the bottom right corner, and the live network statistics in the top right corner. As the patrolling task agent reaches the far end of its path, the direct link begins to fail. Meanwhile, our system is able to maintain stable communication by routing packets through the intermediate network agent. In conclusion, our system delivers wireless infrastructure on demand to a team of task agents collaborating to complete their objective. It is task agnostic and can be applied to any multi-robot system that requires communication, and is useful in practical scenarios, running on board a standard robotic platform with modest hardware specifications and a common 802.11 Wi-Fi compliant communication device. Thanks so much for watching.